Okay, well, thank you so much for the kind introduction, Rafael. This has been a little while. And so my talk is approaches and challenges to virtual and augmented reality in healthcare. As you can see my slides, I assume. And as Rafael said, I'm a professor at the Instituto Superior Técnico, the Universidade de Lisboa. And this is, I'm interested in virtual augmented reality, multimodal interfaces, graphical modeling, among many other things. And this is something that I've researched that I've been doing with my colleagues here, more recently with Catarina Moreira, the AI part on AI&XR. We have a project ongoing called Xavier on extended reality for analysis and AI for analysis of chest radiographs that I'll be talking a little bit. And of course, my colleague Anderson Maciel is an associate professor with habilitation in the Instituto Superior Técnico and is also interested in virtual reality and haptics. Indeed, I'm talking to you from Orlando, where VR 2024 is taking place. So, yeah, currently we are doing research on medical AR, VR, AI. Indeed, we are organizing an actual seminar next year in January, and together with Katarina and Anderson and Wolfgang Hurst, we are organizing a conference on IEEE AI XVR. So there's an interesting convergence of artificial intelligence and extended reality. And of course, anybody that does research on extended reality will ask you, what is extended reality? Well, 50 years ago, a guy called Milgram came up with this idea. There's a continuum between real reality, which was something that I always found funny as a term, and immersive VR, where we have diminished reality for people who suffer too much from motion sickness, for instance. Spatial IR, that's the thing where you can see projections in the facades of buildings, see through AR. That's what we have currently with things like magic leap glasses, for instance. We have augmented virtuality, where people like to see a video of their surroundings while they are immersed in virtual reality, so that they don't stumble on the furniture or get to see where the cup of coffee is. And then we have semi-immersive VR for people who like to work on tables. I'll show you some of that in a minute. And of course, we have real immersive VR. And we call this usually mixed reality. And the idea that we can go from real reality to immersive VR in a seamless continuum, it's what we call extended reality to incorporate all these concepts. Um, so the challenges for us for a number of years have been to build a network of healthcare professionals, which we are. We have a good relationships with the physicians and clinical people and surgeons from Duke University down to Tanzania, going through Lisboa in healthcare group Lusíadas and other institutions. Of course, it's interesting when we try to develop applications for physicians or for healthcare for surgeons. There's kind of a linguistic barrier, and somehow people expect us to do the impossible in 2 hours or less. Of course, that works in Hollywood, but not here. The motivation for most of our work is that there are lots and lots and lots of medical images, but we want to get away from the 2D realm of screens. And we want to, instead of being able just to see coronal, sagittal, and transversal planes, to look at things in 3D. And with augmented reality and extended reality, we can really see things and teach things like anatomy, medicine in a more engaging way. And right now, one of our major directions is using extended reality for collaboration across cities, continents, and even the Earth. Let me present you 3 or 4 projects that we've been involved with, some of which started when Rafael was in our group. One is radio diagnostics, the idea that you can use virtual reality to improve viewing conditions. We published a paper a number of years ago, already too many to recall, called Virtual Reality for Radiologists in the Reading Room, or VROOM. And the idea is that reading radiographs is still pretty much of a difficult art. And people worry about some things like having the proper illumination, looking at the right data set in the right way so that they don't confuse highlights on the screen for features or malignant formations. And we figured out if you put a headset on people's heads, you can control illumination and parallax in one fell swoop. And thus, this VIV room was born. And Mauricio here, who finished his PhD a couple of years ago in my lab, is showing the problems with radiology in a conventional room, adjusting the lighting, adjusting the perspective. And you can solve that by using virtual reality. Notice the frame on the table. The idea is that you can capture work on it at the table and still use your hands, not to have them suspended in the air, but having the hands resting on a table, which is much more comfortable than playing Tom Cruise in Minority Report, for sure. And this is an example of a minimalist interface where you can navigate the 3D slices of a data set and rotate the data set, all in a controlled viewing and illumination condition. And thus you can see, or you can simultaneously control the rotation and navigate through the slices of the data set using simple hand gestures that are captured by that frame I showed you at the beginning of the video here. So you can do things like adjusting brightness, that's the control that you see on the screen, sliding, using an horizontal sweeping gesture with your fingers, or navigating through slices using other movements. And there you see. So you have a simple horizontal, vertical gestures that are very easy to issue and learn. And the interface was deliberately kept minimalistic. And of course, you can change scale, zoom into the set. We've been playing with these ideas on improving this using body movements for the next iteration of our prototype. So to summarize, we did an evaluation, an experimental evaluation for radiologists, different, actually 6, sorry. 5 of them had no experience in VR, from very different specialties, from radiology to neuroradiology, gynecology, obstetrics, surgery, and dental implantology. And they appreciated the fact that even though the resolution of that Oculus headset was not fantastic, they could see the possibilities, and more important, they were able to identify the lesions without being prompted to do so. We are working now on an improved version of this prototype to get clinical certification with a medical device company, and the precious help of a general physician that has been giving us interesting insights. Another interesting topic that we've been working on is virtual colonoscopy. You know, colonoscopy is really an unpleasant exam. I hope nobody that is attending here has ever experienced it. And our idea is to replace the insertion of a tube to watch for malformations in the the large intestine can be replaced by doing a non-invasive CAT scan or MRI. We are now focused on MRI because the surgeons that we've been working with advised us that they do not like to work with ionizing X-ray radiation. So we are going for magnetic resonance instead. But you know, the idea, the problem is that you have to navigate through, when doing virtual colonography, which is the desktop exam, you have to navigate to 2D slices, and it's difficult to identify formations, and this can be problematic in a traditional desktop environment. So we decided to work on improving interaction techniques for immersive colonography, and we published this in MICAI a while ago, and now I'm going to show you just the reconstructed surface. We use computer graphics software to provide a reconstruction of the inner walls of the colon as a surface, and then it can be the clinician can navigate the colon inside and looking for malformations, be there polyples or the verticals. As you can see, it's possible to recall the original data set and have an idea where the person is located in there. Again, we did a preliminary evaluation with five male and 2 female doctors, and one of the things they liked about this was that the diagnostic would take minutes instead of hours, and they love the idea of immersion and using your head to control the point of view, having a freedom of movement, and be able to navigate the structure using a world in miniature gadget. They decried the limited camera control and identified the number of improvements are needed. And this is where I should bring to your attention the fact that we are now working on with better high glasses. I'm also working on this project in the context of a nationally funded initiative that Xavier, and that's the 3D part of the project. I'll tell you about the 2D in a minute or so. And we believe that combining AI, machine learning techniques with 3D graphical reconstructions, we can improve the diagnostic in very meaningful and interesting ways. And this is an example of the features you can do. You can see the world in miniature. That's the part over highlighted in green. And these are a more recent version. The yellow line is the medial axis line, so you can always use that as a support for navigation. And you can jump from parts to parts in the column. You can create a list of bookmarks where you identify interesting features, measuring distances. And now the interesting part that we are using eye tracking so that clinicians can toggle on and off a colored representation of the inner colon to see the parts that they have visited more thoroughly in blue, the ones that they have just glanced on, and the unexplored parts in red. And you can switch between these two features and also can see them in the world in miniature to make sure that you visited all the interesting parts. Here you see what I meant about highlighting the world in miniature with the different colors so that the clinician knows where she has been. And of course, you can recall the original data set. And this is a more recent example that I will skip for the sake of brevity. And now for the AI part, the artificial intelligence. So why are we bringing artificial intelligence here? And this came out of an observation and talks while I was on a sabbatical in New Zealand and talked to clinicians there. And later with Professor Catarina Moreira, we have been working on this idea of combining eye tracking, artificial intelligence, and virtual reality to improve diagnosis. So what can we learn from eye tracking data? Well, the idea is that we can use deep learning to extract features, make classifiers. But the question is, can we use machine learning to make good predictions or help clinicians in diagnosis? Problems is that sometimes machines can make the right predictions, but not for the right reasons. And sometimes the classifiers can mistake features of a collapsed lung for something that's just fat. Actually, the breasts on a female patient. And those things that we as non-experts look at the naked eye, we would blindly trust the machine classifications. The radiologist, the real experienced radiologist looks at the image and says, no, that's totally wrong. I mean, the person has a telangiectasis, but that's not there, and that's the incorrect diagnostic. So we have first to contend with incorrect predictions made by radiologists, and machine learning saliency methods tend to perform worse when compared to experienced humans. And there's another problem, racial biases and other sources of biases also bring confusion to medical diagnostics. So we are focusing on having an explainable AI approach where you would get a diagnostic, and then you could twist the machine until the machine is forced to confess what features in the data in the radiograph have led it to arrive at those conclusions in a way that a human expert could question, or that could be used to teach medical students. And thus, the project called Xavier, Explainable AI and VR for Enhanced Radiologies that we started a year ago. It's also going on under UNESCO Chair on AI and VR. That's a joint project by Professor Catarina Moreira and myself, and we are looking at eye tracking. And following the conversations I had with Dr. Colin Simpson, a clinician in Wellington University when I was on sabbatical there, the idea that we are pursuing is that we can look at eye tracking features. Now that we have lots of mounted displays that feature eye tracking, we can use the saccades, which are short duration movements that can quickly go from one point of the visual field to the other, and fixations, which are slow movement eye positions where of the image where the eye tends to linger more, and look at the correlations of these eye tracking movements, combining them with deep learning to build cognitive maps of what the radiologists are doing, investigate the relationships of their eye movements with other things that have not to do with the diagnostics proper, such as the influences of fatigue when people have been looking at images for far too long, and cognitive load when they are puzzled by what they see in the images or by the user interface. And then we want to investigate how radiologists that are trained in different countries can access these different images and according to their degree of expertise. And this is an example of eye tracking that you can use commonly. Eye tracking is used to assess the usability of web pages, but it can, and then you can see the patterns of fixations and saccades when people are navigating, for instance, a web page. And as you can see, it's kind of a chaotic movement, but from eye tracking fixations and saccades, you can see what interests people on an image and what the order in which they visit them. And here you can see the typical application of using that to assess the usability of a web page. And if you look at these three radiographs, I would let you to ponder for a moment. This is the, you can distinguish the expertise and ability of people looking at radiographs just by checking their eye patterns. They were starting students, middle people with some training, and experienced radiologists were asked to look at the same image and to identify the lesions. And as you can see, the starting students are totally confused. They don't know what they are looking for, and thus they scan the image in all directions. That's the right image. And then you have the middle image where you can see that people who have some training already could arrive at a diagnostics. And on the left, you have the specialists. After a quick glance, they know what they're looking for. They identify the lesion, they move on. And so these are the patterns in eye tracking data that we are looking at. And we have annotated data sets from the public domain, Mimic and Reflex. We're using this. And with the help of one of our master students, we were able to build uh, uh, temporal attention patterns. What you see here is a Markov chain model that shows the transition of the eye between different chest areas. And there you can see the real-time evolution. And what you are looking at here is not the high patterns for a single image, but the high patterns collected across 1,035 different images and integrated. The width of these connections identifies how long people have been looking at, and the flows represent how often people would transition from one area of the radiograph, one anatomical area, to another one. And these anatomical areas are identified by rectangles here, and each rectangle in the image corresponds to one of these blue boxes. And we are still looking at this. And the idea is that we are going beyond just looking at the images by themselves, which is a common trap that many radiologists fall, but incorporating clinical data. And we have published several papers on the topic, one of them in Nature Scientific Reports, describing how incorporating clinical data and X-ray images to improve accuracy in diagnostics. And our goal on this project is to move towards human-centered deep learning architecture. And this is an example of an eye tracking collection application. And of course, you have interesting sorts of problems, but I'll leave you with one interesting thought. How we thought that radiologists would look at images, it's totally different from what they actually do. You notice these ellipses in red here, and these are the areas of the thorax where an experienced radiologist identified lesions that need attention and then correlate with pathologies. And the areas in blue and yellow and red identify the most glanced at parts of the radiograph that they looked at. So as you can see, there is a zero correlation apparently between what the radiologist was looking at and the patterns she identified. And this brings us to an analogy that comes from World War II of the Royal Air Force that was trying to assess the parts of bombers that they should reinforce the fuselage so that to increase their survivability rate. And they thought wrongly that the parts of the fuselage that had most holes in them were the ones that needed more attention and for the fuselage to be reinforced. They called the statistician to look at these images, and the statistician said, "No, you are totally wrong. The parts of the fuselage with more bullet holes in them are the ones that the airplane can survive and still keep flying. You should still reinforce the fuselage in the parts that have no bullet holes, because what that means is that the planes that were shot down were probably hitting those parts and they never made it back." And so we are looking at a similar insight, which has yet to arrive in our research. But as Werner von Braun used to say, research is what I do when I don't know what I'm doing. And here we have ample opportunities for research. And this publication and part relates to using clinical data in conjunction with X-rays, where we combine the tabular data with X-ray images and try to get a neural network to improve its classification rate. And we have had some promising results. Some of this work is currently being considered for publication, and others have been already published, such as the one that I'm showing you, where our MDF net is the name we gave to the approach that combines image data and clinical data. And as you could see, it improves on current purely image based diagnostics. We are looking at whether radiologists have a pattern, and we did find patterns across thousands of radiographs using the public domain data sets, but still ongoing there. And part of this work has to do with our students, Chi Cheng Xie, who's a PhD candidate at QUT, and two of the six master students that have already finished, Andrea Luiz and Diogo Alvito. Okay, I'm running a little bit out of time. Feel free at any time to ask questions, but we can save them for last as well. One other project that we are focusing now is to use augmented reality for teaching anatomy, and I'll try to zip quickly through this slide. So anatomy is the foundation of medicine, and this is a famous Rembrandt painting describing a surgeon teaching in an anatomy class using a cadaver. Often criminal-based cadavers were used for dissection, which explains the fact that this cadaver has two right arms, in case you noticed. And this is another picture illustrating the idea of having anatomy students around this dissection table and having this kind of shared perspective over the anatomical structures that the master is illustrating. Main problems with the classical approach to anatomy is that there is a shortage of cadavers with the proliferation of medical schools in the last few centuries. And the cadavers are usually only good for one dissection because to show some anatomical structures, you have to destroy others. And so here enter anatomy studio, um, a prototype that uses a cross reality. Now, the idea of cross reality is that you can use different applications in different versions of the Milgram continue, remember, from real reality to immersive reality. And here you see a tablet showing sections of a cadaver. I'll explain where the cadaver came from and how we can use digital cadavers to improve dissection and make them reusable. And here you are seeing augmented reality, mixed reality glasses from a now defunct company called MetaVision. And these images come from an augmented visible human project. There are three instances of this project, one in Korea, another in the United States, and another in China, where corpses of deceased patients are frozen and then cut into thinly slices using a microtome. Each slice is photographed in high resolution, and then you make the whole data set of 5,000 something slices available, and you can perform reconstruction. Here is an example of the slice where you can see two arms and the torso, lungs, the spine here, and a blue thing here. The blue thing formations are, of course, ice. And these are very thin slices cut with the help of a specialized instrument called a microtome. And this is what you can do on a tablet. You can trace contours, and then across multiple slices, you can identify an anatomical structure of interest. And this is a block diagram of the system. So you can see two different people using augmented reality headsets that connect to an anatomy studio server where the slices and are stored. And then you have tablets and you can issue contours and make a 3D reconstruction. By the way, Rafael did work a little bit on the reconstruction part, and this is the result of making a 3D reconstruction of some structures using this approach. And here I have a small video that shows how you can use mixed reality to navigate through the data set. How you can copy a slice from the augmented reality perspective to a tablet, and now you can, on the tablet, you can highlight contours, making zoom and rotation, etc. And this can be done in a collaborative fashion. And the idea from our colleague Jean-François Hull in the University of Paris Descartes in France, who collaborated with us on this project, is that you can teach anatomy by having students performing reconstruction of anatomical structures the way you are seeing here. We did a user study with 8 medical professionals and 2 students, and could identify the different interactions that people can work here with a tablet. Mixed reality preview, that's the second slice. Mixed reality exploration, where people twist their bodies and look around the data set. Interaction, and the interesting part here is collaboration. We are working on a virtual reality extension of this project, motivated by the recent pandemic, so that people can use virtual reality to work not on the same room, but across different continents. And this was the work done in part in collaboration with UNESCO Chair of Digital Anatomy, and we published a couple of years ago a Springer book on digital anatomy that has received some attention. Okay, for the sake of brevity, I will skip over what we mean by taking XR to the operating room. So far, we've covered the diagnostics using AI and XR for improving X-ray diagnostics. And now our long-term goal is to take extended reality to the operating room to improve surgical planning and surgery proper. Problem with taking user interfaces to the operating room is that you cannot touch the keyboard or the mouse because you are working on a germ-free environment, and the keyboard and the mouse are the most germ-contaminated parts of our tablets and computers. So we have been working on using gestures captured from afar to keep the environment sterile, and the other part is using the feet for selection. Here you can see a dental surgeon using the feet. I don't have time to explain all the details here, to navigate a data set without touching the screen, mouse, or keyboard. And what are we going to do with this? Well, our idea is to augment the surgery by using these touchless interventions. We have an ongoing project on augmenting laparoscopy, or minimally invasive surgery, using augmented reality. And the idea here is to improve the conditions of work for the surgeon and for the team. This is a typical setup for a minimally invasive surgery, where the surgeon is not looking at where her hands are or where the instruments are, but they are looking at a monitor, and this creates some interesting eye coordination problems that we are trying to approach by using augmented reality headsets, and then improving the conditions of work. This is a movie that we took in operation in a clinical facility in Lisbon. And this is, you can see how the surgeons operate. So looking at the laparoscopic video from a camera is kind of uncomfortable. You have to twist your neck. You have to learn eye-hand coordination again. And another paper where we published, where Rafael was also a part, we discussed that people looking
at a screen from different perspectives can sometimes be misled by gesture references. What I'm pointing at is not what you're seeing me pointing at, and that can create confusion. And that's the issue. That's an interesting paper that we published a couple of years ago about working basis. And there's another problem that you cannot go back to the patient data during the surgery. So this was an interesting work on laparoscopy with augmented reality adaptations that focuses on using, again, mixed reality glasses. And there you can learn a new modality of minimally invasive surgery by having the possibility of the surgeon looking at where the instruments are, not at the screen on the wall, and then taking advantage of eye-hand coordination. Now, the interesting part here is that the surgeon can twist their head to the right, and they can navigate the data set from this patient without having to ask for an assistant to bring up the data set on the screen. And this is an interesting technique that we are looking at. We put a mouse, a Bluetooth mouse, in one of the surgical shoes used by the surgeons, and use the navigation techniques with the feet that I showed you on the previous video to enhance the interaction during operations. This is, of course, a simulated video, but it's pretty much an area of interest for us. We are currently working actively into this and working with colorectal surgeons to improve this work. Why aren't we using robots? Well, robots are very, very, very expensive, and they are only used in 5% of minimally invasive surgeries. So we believe there's a bright future for augmented reality in the operating room. So sorry about the loud music. We are coming to the conclusions part. So we believe that the future for AI and augmented reality in the operating room includes a merging cross fertilization of different techniques, including Internet of Things for distributed uh, data collection and tracking, focuses on ergonomic and hygiene applications and germ-free interfaces. Investing in advanced UIs, there's an opportunity for doing using the sense of touch, which is something that we have not explored yet, but that I've been discussing with Professor Anderson Maciel a lot about using the physician's hands to feel the organs that they are touching and that they are exploring during surgery. With Professor Catarina Moreira and our PhD students, we have now 5 PhD students on this project. We are looking at different aspects, including explainable AI and large language models. That's for teaching anatomy in a very different way, and using full body language in ways that only augmented reality techniques can afford. So, to conclude, we see plenty of challenges ahead, and the head-mounted display technology is still suffers from lots of non-standard equipment. We're looking at still at some cyberpunk-like contraptions where the ways to interact with the data and the visualizations are not exactly the same. And from the point of view of user interfaces, augmented reality and extended reality are to the automobile as this vehicle of 150 years ago was to modern car interfaces, where you would turn there was no steering wheel, you would turn the control surfaces in funny ways to achieve locomotion. And of course, the problems with virtual reality that are well known, including disorientation, fatigue, and sometimes cyber sickness. But we believe there's a bright future ahead for this family of user interfaces. And maybe there's a bright future for us
for the combination of extended reality techniques, artificial intelligence, and humans, of course. And there have been a lot of people involved in our past projects, and I've yet to mention here our current PhD students, and you can see here people from our extended network of collaborations. And I will stop here and do not go more in detail into different design disciplines. Thank you for your attention.
Right. Thank you for the talk. It's good to see what you've been up to since the last time we spoke. If anyone has a question and you want to send to the chat, or you want to just ask, just raise your hand and go ahead, Faisal.
Yep, feel free.
Yeah. Thank you. That was a fantastic presentation. Yeah, an incredible amount of work that you sort of relayed to us there in a short space of time. So I'm just trying to gather my thoughts on some of this. What I'm interested in, given the sort of challenges that you highlighted, which I fully agree with, I'm interested in sort of your predictions about how long it will take for us to sort of turn these types of technologies into everyday practices for surgeons. So we can take whatever example you sort of feel is the nearest term to actual everyday usage. I'd like to hear your sort of thoughts about that.
Okay, well, that's a very interesting question, and thank you for it, because it touches in all directions of the work that we are looking at. So right now, we are, let's start with the low-hanging fruit. So right now we are starting a project proposal of an industry-led project with a medical instrumentation firm so that we can certify the use of head-mounted displays as bona fide diagnostic tools. Because the challenge there is that if anything goes wrong and you try a new diagnosis technique, you can expose yourself to malpractice, surgical malpractice suits, lawsuits. And so radiologists are very reluctant to use non-proven techniques unless they can follow practices that have been certified, and they can say, no, I was just following approved practices. This is tried and true stuff. And there is, so first step, certify the use of head-mounted displays as medical instruments. That's we are talking about 1 to 2 years, and the main work to be done there is to conduct clinical tests with many physicians. So that's the vroom part of it. The more researchy stuff, we are now our ambitions with the X-ray analysis project is to I think we are getting somewhere in we are getting interesting results in combining clinical data with X-ray data for AI machine learning classification. We've already showed that there are possible to use good improvements. And the interesting part about that is that we got the insight from radiologists. And what we are doing now with them is to come up with new classification algorithms that combine this. And we are using, okay, the part that I didn't talk to you about, we are using large language models to generate synthetic data to enhance the predictive power of neural networks. Maybe Professor Catarina Moreira can talk about that. It's a whole new universe out there. Maybe we can get, we are getting excellent results with PhD students, and that's probably, I think 1 or 2 years in the future, we might get some usable stuff. Now, the more challenging stuff in terms of getting to apply this in practice is augmented surgery. There, you experience problems because you cannot, if you might envision problems with using non-standard diagnostic tools, imagine if anything goes wrong during a minimally invasive surgery,
and people blame your augmented reality headset because the batteries went off mid-time to surgery and the surgeon cut something that he shouldn't or she shouldn't have cut. Gosh, the possibilities for getting a huge lump sum indemnification are endless. So there you have to tread a more careful path. You need to demonstrate the usage of this augmented reality technique in mannequins, then you operate with pigs, and finally you get to the operating room after you negotiate time and time again with the ethics approval board from our universities and the hospital. Now, another interesting project that I didn't have time to talk about is using telemedicine, where you can use remote experts to collaborate with local clinicians, surgeons in a telemedicine environment. This is fascinating. I've seen some prototypes used for training here at IEEE VR, but as a colleague of mine told me, collaboration in VR is the most fascinating research topic because it's not going to work for the next 20 years, and we can still going on published paper year after year, paper after paper. It's a guaranteed career path for young PhD people. So I'm sorry if this was too long-winded.
No, that was great. Yeah, thank you very much for your answer. We definitely need to have a follow-up conversation at some point, which I'll instigate over email. Thank you.
For sure.
I got a question on. So I haven't heard about the eye tracking project that you were working on. It's very interesting. I think very good use of eye tracking. Is it the main direction of travel, the training and trying to do automatic diagnostics, or do you think you could, well, after you identify those patterns, right? So this is how an expert looks at a scan. Is that something that then you can use for training, or something that you can use for, you have a student or you have someone else, the same way that you have the heat map on the colon saying this, you looked here, you could have something that says you should look here. Is that something you have in mind for the future?
Professor Catarina Moreira is working with me on this Xavier project. I would let her answer some of that. If
you're on mute.
So pretty much we have here a couple of directions on the usage of eye tracking. So all the motivation of this, like Professor Jorge said during the presentation, is that deep learning is it's only looks at pixels to make inferences about potential lesions in X-rays, and there is nothing more subjective as radiology. So we thought that eye tracking could be a fantastic way to capture experts' cognitive patterns and try to teach them to younger students, in the sense that, for instance, when they are learning to observe a shadow or try to understand what's a consolidation, they can try to look at certain images, or if they miss something, we can have a pop-up or an intelligent user interface saying, look, the majority of the experts look here. Are you sure you're not missing anything? Because the thing that usually students suffer when they are in the beginning is that they have this anchoring bias. So they recognize something and they focus their vision there instead of still traversing the entire X-ray. And this is a potential use case that we can use. And again, to train students in the sense that you missed here, or most people looked here, or careful because this was confused by something else. The other use case is precisely here to enhance the classification and lesion detection of current classifiers. Again, having this human-centered component instead of this pixel and human agnostic component of current architectures.
Good, thank you. That's very interesting. Yeah. Anyone else? If you have any other questions, you can send chat. Or well, I think did you have your email? Oh well, I think you have your contact information on also the event. People can email their questions as well. I know some of the people silently watching are doing some research that is related to what you talked about, they might follow up later.
Yeah, sure. Feel free to send me email. We are finalizing a couple of websites on the Xavier project and the UNESCO Chair. I will send the contacts to you, Rafael. You have my email there. Professor Catarina can write hers because it's longer than mine. And it becomes a problem to write and to talk and type at the same time. But yes, we are very, very interested now in using these techniques to enhance collaboration. There will be a Dutch Tool seminar and the IEEE conference in January next year. If you want to know more about that, please page us. It's called AI&XR. The conference, we are organizing that in Lisbon in January 25 to 27. In case you want to know, maybe I can even type the URL for that one. Either I or Professor. Oh yeah, we have that AI&XR at technical.lisbon.pt. Let me just recover the window here. So more information on that in this URL, please.
Thank you.
Please submit, please come, and please let's stay in touch.
All right. Thank you very much. It was conscious of time. Let's wrap things up. And this is recorded for everyone else to watch. And thanks for everyone that